Hi, my name is TTJ Kepsi Richard and welcome to my YouTube channel. Today our discussion will be on indices. Before the lesson will end, I will introduce you to indices. I will also tell you what some basic laws covering indices and their application. We will also talk about some basic properties covering indices and their application. Then we'll learn how to express numbers in their index form using prime factorization. This will be a very interesting engagement, so please watch the video to the end. Indices comes to mind when numbers are expressed in this form. So when they are expressed in this form, the A is called the base, okay, and the M is the exponent. The exponent or the index. People also refer to it as power. It's the same. So we can call this, we can write this as A exponent M. So if we have 5, this, we can say 5 exponent 2. And what does it mean? It means multiply 5 by itself twice. So 5 times 5. So if I have 3 exponent, let's say 5, it means we'll multiply the 3 by itself 5 times. So 3 by 3 by 3 by 3 by 3. So in the same way, if I have 4 times 4 times 4 times 4 times 4 times 4, I can say this is equal to 4 exponent 6. That's 4 multiplying itself 6 times. I hope you understand the concept of indices. The next thing we'll talk about is some laws governing indices and their applications. Okay, so the next thing we'll talk about is some laws governing indices. They are very, very fundamental in understanding indices, so please take note of it. So if I have, let's say, 5 exponent 3, okay, times 5 exponent 2. Now 5 exponent 3, from what we learned, it means 5 multiplying itself 3 times. So we say 5 by 5 by 5 3 times 5 multiplying itself twice. So 5 times 5. So this can be written as 5 times 5 times 5 times 5 times 5. So writing this in an index form will be 5 exponent 5. That means 5 multiplying itself 5 times. So look at it. When we have 5 exponent 3 times 5 exponent 2, we have, after expand, we have 5 exponent 5. What happened? It means that when two indices are multiplying with the same base, we repeat the base and add the exponent. That's, this will be 5 exponent 3 plus 2, which is equal to the 5 exponent 5. So if I have 6 exponent 8 times 6 exponent, let's say 4, it will equal to 6 exponent 8 plus 4. And 8 plus 4 is 12, so that will be 6 exponent 12. So we can conclude that if we have a exponent m times a exponent n, it will equal to a exponent m plus the n. So take note of it. This is the first law governing indices. The first law. That when two indices are multiplying with the same base, we add the exponents. Okay. So now let's look at another law. So if we have 2 exponent 5, okay, divided by 2 exponent 2, which we can rewrite as 2 exponent 5 over 2 exponent 2. When we expand this, it means 2 multiplying itself 5 times. That will be 2 times 2 times 2 times 2 times 2 over 2 multiplying itself twice. So 2 times 2. So we can say these two will divide these two also divide that. What is left? We'll be left with 2 times 2 times 2, which can be rewritten as in an index form as 2 exponent 3. So look at it, when we're having 2 exponent 5 divided by 2 exponent 2, after expressing we have 2 exponent 3. So it means that when two indices are divided with the same base, we just repeat the base and subtract the exponent. So that will be 2 exponent 5 minus 2, which is 2 . So we can conclude that you have a exponent m divided by a exponent n. It can be written is a exponent m minus n. Please take notice of it. We'll be using it very often, so take notice of it. Okay, so now look at it. When we have, let's say, 2 exponent 3 all exponent 2. So 2 exponent 3 exponent 2 means what is in this bracket, we multiply it by itself twice. So we can say this is 2 exponent 3 times 2 exponent 3. Then this, it means we multiply the 2 by itself 3 times. Then 2 exponent 2 times 2 times 2 for this. Times this 2 multiply itself 3 times. So 2 times 2 times 2. So we will have 2 times 2 times 2 times 2 times 2 times 2, which can be written in an index form as 2 exponent 6. That's 2 multiplying itself 6 times. So look at it. When we are having 2 exponent 3 all exponent 2, after simplifying it we have 2 exponent 6. What does it mean? It means that when an index or an indices is being exponented again, the exponent will multiply what is being exponented. So this is 2 exponent 3 times 2. That's how can we have 2 exponent 6. So if I have 5 exponent 3 exponent 5, it will be equal to 5 exponent 3 times 5, which will be 5 exponent 50. So we can conclude that if we have a exponent m, all exponent n, it will be equal to a exponent m times n, which is a exponent m n. Please take notice of it. It's very, very important. So these are the 3 basic laws governing indices. The first one, when 2 indices are multiplying with the same base, you repeat the base and add the exponent. Then when 2 indices are divided with the same base, you repeat the base and subtract the exponent. Then this, when an index number is being exponented again, we multiply the index by the exponential. That's this. So a exponent m, all exponent n, will be a exponent m times n. And that's how we have a exponent mn. Now we'll apply all this in solving some sample questions. So come with me. So let's solve our first question by applying the laws. So a exponent 3 times a exponent 5 all over a exponent 6. How do we solve that? See, these 2 indices are multiplying with the same base. So what we do? We repeat the base and add the exponent. So we can say the top will have a exponent 3 plus 5 all over a exponent 6. So what we have, our a exponent 3 plus 5, we have 3 plus 5 is 8, so a exponent 8 all over a exponent 6. We can rewrite this as a exponent 8 divided by a exponent 6. So what do we do? they are dividing, so we subtract the exponent. So that will be a exponent 8 minus 6, which will be equal to a exponent 2. So we can conclude that our a exponent 3 times a exponent 5 all over a exponent 6 will be equal to a exponent 2. I hope you get that. We'll solve another one so that you get a concept. So we'll solve our second question. They said we should simplify 3 exponent 4 times 3 exponent 5 times 3 exponent 2 all over 3 exponent 6 times 3 times 3 exponent 3. So I might say this 3, that since it is written like so, it means 3 multiplying 1. So 3 exponent 1, we can say that. So remember, we said when 3 indices are multiplying with the same base, we add the exponent. So this can be written as 3 exponent 4 plus 5 plus 2. All over this can be 3 exponent 6 plus 1 plus 3. So what are we having? 4 plus 5 is 9. 9 plus 2 will be 11. So I have 3 exponent 11 over 6 plus 1 is 7. 7 plus 3 is 10. So I have 3 exponent 10. This can be rewritten as 3 exponent 11 divided by 3 exponent 10. So when two indices are dividing with the same base, we just subtract the exponent. So that will be 3 exponent 11 minus 10. So this will be 3 exponent 1 equal to 3. So we can say 3 exponent 4 times 3 exponent 5 times 3 exponent 2 all over 3 exponent 6 times 3 times 3 exponent 3 is equal to 3. I hope you get that. We'll solve another one so that you get a concept. So let's solve our third question using the laws. So this one is not difficult if you apply the law. So we'll apply the third law that we look at in solving this, including, so we'll apply all the 3 laws to solve that. So remember, when an index number is being exponented again, we multiply the index. So this can be written as 5 exponent 3 times 4 times this one too, 5 exponent 4 times 3 all over the middle, just what is in the bracket. We have 5 exponent 2 times 3, then exponent 2 again. So what are we having? This will be 5 exponent 12. 3 times 4 is 12. Then 4 times 3 is also 12. So 5 exponent 12. Over 2 times 3 is 6. So that will be 5 exponent 6. Exponent 2 again. So this, we apply the third law again. So we have the top, the numerator 5 exponent 12 times 5 exponent 12 all over 5 exponent 6 times 2. So what are we getting? We'll get 5 exponent 12 times 5 exponent 12 over 5 exponent 12. So we apply the first law. Two indices are multiplying with the same base. We'll just add the exponent. So we get 5 exponent 12 plus 12 over 5 exponent 12. 12 plus 12 is 24. So we have 5 exponent 24 over 5 exponent 12. This is dividing. So we can just rewrite it as 5 exponent 24 divided by 5 exponent 12. So two indices are dividing with the same base. We subtract the base. We have 5 exponent 24 minus 12. So 24 minus 12 will be 12. So we have 5 exponent 12. So we can say the answer to this our question is nothing but 5 exponent 12. I hope you get that. I hope you get that. The next thing we'll look at is some properties governing indices and their applications. So now we'll talk about some basic properties. Look at it. If I have 2 exponent 4, it means 2 multiplying itself 4 times. We'll get 16. 2 exponent 3, 2 multiplying itself 3 times. we'll get 8. Then 2 exponent 2. 2 multiply itself twice, we'll get 4. 2 exponent 1, that will be 2. Now look at it. See, as the exponents are decreasing, that 4 decrease to 3, 3 decrease to 2, 2 decrease to 1. What is happening to the answers? Look at it. 16, 8, 4, 2. You can realize that the previous answer, to get the subsequent one, you divide the previous answer by the base. So 16 divided by 2, 8. 8 divided by 2, 4. 4 divided by 2, 2. The same vein, if I have 3 exponent 4, 3 exponent 4, that means 3 multiplying itself 4 times. That will be 81. 3 exponent 3, that will be 27. 3 exponent 2 will be 9. 3 exponent 1 will be 3. So if we have 3 exponent 4 equal to 24, we need 3 exponent 3. We just 3 exponent 4 equal to 81, and we need 3 exponent 3. We just divide 81 by the base, which is 3. 81 divided by 3, 27. To get 3 exponent 2, we divide the subsequent one. 27 by 3, 9. To get 3 exponent 1, we divide this by 3. So 9 divided by 3 is 3. Now, if I need this, so the same thing applies to the first one. If I need 2 exponent 0, what value? I'll just divide this answer by the subsequent. So by the base, so 2 divided by 2, that will be 1. The same way, if I need 3 exponent 0, I'll divide this answer here by the base. 3 divided by 3 is 1. What is the meaning? It implies that any number exponent 0 is 1. Any number exponent 0 is 1. So we can conclude that a exponent 0 is equal to 1. It's a basic property. Please take notice of it. Any number exponent 0 is 1. So we want to use the basic property which says that any number exponent 0 is 1. So look at it. They say we should simplify this. So we look at all this is being exponented by 0. So we can say all of this is 0. It doesn't matter the answer we'll get. Exponent 0 will be 1. So 100 exponent 0 is 1. 1 million exponent 0 is 1. So we can say the whole of that is 1. 1 times 2 exponent 3 over. The whole of this will be 0. 12 exponent 0 will be. The whole of this will be 1. Because 12 exponent 0 is 1. So we can say 1 times 2 exponent 2. 1 times that, 2 exponent 3 over 2 exponent 2. So what do we have? They are dividing. We can rewrite this as 2 exponent 3 divided by 2 exponent 2, which is to apply the law, which says that when two indices are dividing with the same base, we just subtract the exponent. So that will be 2 exponent 3 minus 2, which is 2 exponent 1, which is 2. So this, the answer is nothing but 2. So please take notice of this. Any number exponent 0 is 1. Now we'll look at another property governing indices. Right. So we want to look at another property. Using the first one, we said to get this answer, we divide the subsequent one by the base 2 as the power decreases by 1. So 16 divided by 2, 8. 8 divided by 2, 4. 4 divided by 2, 2. And 2 divided by 2 will be 1. Now to get, when this exponent decreases by 1 again, what are we having? We have 2 exponent negative 1. So what do we do? To get that, we divide the subsequent answer by the base, which is 2. So that will be 1 divided by 2. That's half. We can rewrite this as 1 over 2 exponent 1. Take notice of it. So this will also reduce again by 1. So we have 2 exponent negative 2. What are we having? We divide half by 2, by the base. So half divided by 2, which is the same as half times, this is over 1. Remember, division. We can change it to multiplication problem by reciprocating. So we get 1 over 4. So you can say 2 exponent negative 2 is 1 over 4, which can be written as, look at it, 2 exponent 2 is 4. So we can rewrite 1 over 4 as 1 over 2 exponent 2. We are building to develop something, so come with me. So 2 exponent negative 2 is 1 over 4, which is 1 over 2 exponent 2. Now let's get another one. As the base decreases again by 1, the exponent decreases again by 1, get 2 exponent negative 3. So what do? To get the answer, we divide this subsequent answer by the base, the previous answer by the base. So that will be 1/4 divided by 2, which will be 1/4 times 1 over 2, which is 1 out of 8. So you can say 2 exponent negative 3 is 1 out of 8, which is equal to 1 over 2 exponent 3. 8 is 2 exponent 3. So look at it, when you have 2 exponent negative 1, it's just writing this. That will become 1 over 2 exponent 1. 2 exponent negative 2 will have 1 over 2 exponent 2. And 2 exponent negative 3 is 1 over 2 exponent 3. Then, if I have 2 exponent negative n, what will I have? It will be equal to just 1 over 2 exponent n. So I can conclude that a exponent negative n will be equal to nothing but 1 over a exponent n. I hope you get that. Please take notice of it. This is another property that will be very, very necessary in this our indices journey. So please take notice of it. So now let's get a concept. We said if you have a exponent negative n, it will be equal to 1 over a exponent n. See, any number written, let's say 2, it can be a fraction with a denominator of 1. So this, we can rewrite this as, this a exponent negative n, you can rewrite this as a over 1 exponent negative n. So this became this, so we can say this is 1 over a exponent n. This implies that, look at it, the denominator became the numerator when it is being exponented by a negative number. The denominator became the numerator, and the numerator became the denominator, exponent n. What I'm trying to say is that we can rewrite this as 1 over a exponent n. Look at it. The denominator became the numerator, and the numerator became the denominator. Then the exponent changes to n, positive, which is the same as 1 exponent n over a exponent n. 1 exponent n is 1. 1 exponent any number is 1. So 1 exponent 1 million is 1. That means 1 multiplying itself 1 million is same 1. So 1 exponent n is 1 all over a exponent n. What is the implication? The implication is that if I have 3 over 2 exponent negative 2, I can rewrite this by changing this problem to have a positive exponent, as the denominator becomes the numerator and the numerator becomes the denominator. Then the exponent changes to positive. So I have 2 out of 3 exponent 2. I hope you get that, which is the same as 2 exponent 2 over 3 exponent 2, which is 4 out of 9. I hope you get that. I hope you get that. So, if I have a over b exponent negative n, we can rewrite this as b over a exponent n. This is another property of indices that is very, very important. So please take notice of it. So these are the 3 basic properties governing indices. So with these properties and the law, we have laid a very good foundation for solving any indices problem. The next thing we'll talk about is how to write some numbers in an index form using prime factorization. So come with me. So I want to write 32 as a factor of prime numbers or prime factorization, using prime factorization. So prime numbers are numbers with just two factors, one and the number itself. So prime numbers include 2, 3, 5, 7, 9 is not a prime number, 11, then in that order. So now, to write numbers as a prime factorization, you find out which prime number can divide this 32 without any remainder. So 2. 2 divide 32 without any remainder. 2 is a prime number. So when 2 divide 32, the answer is 16. So you can say 2 times 16 will give us 32. Now, this 16 is not prime, but 2 is prime. So we find another prime number. One that can divide the 16 without any remainder. That prime number is 2. So 2 divides 16 8 times. So that will be 2 times 8 is 16. 2 is a prime number, 8 is not. So which prime number can divide 8 without any remainder? It's still 2. 2 times 4 is 8. Or 8 divided by 2 is 4. Now, 4 is not a prime number. So which prime number can divide 4 without any remainder? 2 again. 2 times 2 is 4. Now, that means that 32 is equal to all the numbers that are not being divided again, or that are prime numbers. So which numbers are prime numbers? See this 2, 2, 2, 2, 2. So we can say 32 is equal to 2 times 2 times 2 times this 2 and times 2. So 32 will be equal to 2 in an index form will be equal to 2 exponent 5. I hope you get that. Okay, this is very interesting. You need this when we are solving some indices problem. I'll solve one more question on this so that I get a concept. So let's write 27 as a factor of prime numbers. So which prime number can divide 27 without any remainder? That prime number is 3. 27 divided by 3 is 9. 3 times 9 is 27. 3 is a prime number, 9 is not. So, which prime number can divide 9 without any remainder? Is 3. 9 divided by 3 is 3. So, now all these numbers here are prime. So we can say that 27 is equal to 3 by 3 by 3. So 27 is equal to 3 exponent 3 in an index form. I hope you get that. I hope you get that. We'll solve another one so that you'll be abreast with it. So I want to write the 625 in an index form. So we'll look for a prime number that can divide 625 without any remainder. That prime number is 3. Is 5. Is 5, sorry. So 5 will divide 625 125 times. Or in other words, 125 times 5 is 625. 125 is not a prime number, 5 is a prime number. Which prime number can divide 125 without any remainder? It's 5 again. So 125 divided by 5 will be 25. Now which 25 is not a prime number, but 5 is. So which prime number can divide 25 without any remainder? It's 5 again. 25 divided by 5 is 5. So all these now are prime numbers. So we can say that our 625 is equal to 5 by 5 by 5 by 5. 1, 2, 3, 4. So our 625 in an index form will be 5 exponent 4. I hope you get that. I hope you get that. We'll end it here. Please remember to subscribe to the YouTube channel before you sign out and click on the notification bell so that anytime I share videos on this, you'll be the first to receive it. Until we meet again, bye-bye.